Good morning, my name is Luigi Fre, and in this demonstration I will showcase the capacities of the TeraFlow cloud-native SDN controller. This work has been done in collaboration with CTPC, Chalmers, Atos, UBTech, Telefonica and Infinera, all of them partners of the TeraFlow project. Software-defined network controllers are the de facto solution to manage the access, transport, and the cloud network segments. Besides, they are the key enabler for configuring the infrastructure supporting the network function virtualization and the multi-access edge computing technologies. However, these SDN controllers usually rely on monolithic software, which in turn inherits the limitations in terms of scalability, flexibility, and availability they suffer of. Network function virtualization aims at moving the network of functions away from proprietary hardware appliances into decoupled and softwareized components running over virtualized infrastructures. Multi-access edge computing aims at providing compute resources at the network edge to deploy virtual network functions near to the users and improve the user experience. Finally, zero-touch automation aims at completely automating the management processes to reduce the deployment and operational time and cost while increasing the traceability, the consistency, and scalability of the infrastructures. The objective of the TeraFlow H2020 project is to create a novel cloud-native SDN controller for beyond 5G networks, overcoming the limitations of monolithic software, among others. Some of the main features that will be released by the TeraFlow OS SDN controller are the integration with current NFV and MEC frameworks, the capacity of managing flow aggregation, the service management, the network equipment integration, machine learning based security and forensic, and multi-tenancy support. This is the architecture of the TeraFlow OS SDN controller. Two sets of components are defined. First, the core components implement the building blocks for the controller, while the NetApps block of components define some extensions in the functionality of the TeraFlow OS SDN controller. The components used in this demonstration are highlighted in blue. In particular, the context management component is in charge of keeping track of the different configurations per device and service. The device component is in charge of interacting with the different network and infrastructure elements. The monitoring component is in charge of collecting monitoring data from the different elements in the infrastructure. The automation component implements some control loops used to implement automatic behaviors in the system. The service component is in charge of managing the different connectivity services, and the compute component exposes a northbound API towards external systems such as an open source Mano or other NFV or MEC frameworks for interacting with the TeraFlow SDN controller. Besides, a web UI interface is provided, which provides both the information of the TeraFlow component of the TeraFlow SDN controller and a Grafana panel with the monitoring data. This figure illustrates the internal architecture of the different components. Among others, it is worth noting that the different components are interconnected by means of a gRPC-based protocol specially designed for the TeraFlow SDN controller, and many of them implement some application programming interfaces for extending their functionality. For instance, database APIs are implemented in context and monitoring component for plugging different backend databases. A driver API is implemented in the device component for extending it with new drivers using different protocols and data models. And the service component implements a service handler API enabling to support different kinds of services within the SDN controller. This is the architecture of the network service considered for this experiment. As it can be seen, it consists of two virtual network functions deployed at different locations that needs to be interconnected. Each of the VNFs consists of two virtual deployment units, one for management and the other for data processing, and the VDUs are interconnected by means of an internal network. The deployment of each of the VNFs At the different locations, it's carried out by the OpenStack Virtual Infrastructure Manager and orchestrated by the open source Mano NFV orchestrator. However, to interconnect the two BNFs, given that they are deployed in different and distant data centers, a one infrastructure manager is needed to perform the connectivity between the data centers. That's the mission of the TeraFlow SDN controller. This is the scenario considered for this demonstration. Here, two OpenStack-controlled data centers needs to be interconnected to establish the network service. Open source Mano takes care of the configuration of the different virtual network functions in the data centers, while it delegates to the TeraFlow controller the configuration of the end-to-end connectivity. To establish the inter-data center connectivity, TeraFlow SDN controller relies on the OpenConfig data model for the configuration of the packet routers and the transport API data model for the configuration of the optical layer. The TeraFlow SDN controller has been deployed on top of Kubernetes at CTPC premises. Besides, both the OpenStack and the open source Mano are deployed also at CTPC premises together with the emulated optical layer. Besides, the packet layer has been deployed at Telefonica premises. The packet layer at Telefonica premises is illustrated in this figure. As it can be seen, two Infinera DRX routers are interconnected back-to-back and connected to a Spirit traffic generator. On the left-hand side figure, it can be seen the two routers connected by means of the blue optical fiber, and on the right-hand side, it can be seen the Spirit traffic generator connected to the routers by means of the orange fibers. A number of workflows have been defined to demonstrate the functionality of the TeraFlow OS SDN controller. When a new device is added, the device component selects the appropriate driver based on the supported protocols and establishes the connection towards the device. Then, the configuration of that device is retrieved and stored in the context database. This creation of device in the context database circulates a number of new device events towards the different components to notify the addition of this device. When the automation component receives the new device event, it first retrieves the current status of the device and its configuration, and asks the device component for the initial configuration in case this device is still not configured. Then it populates the initial configuration template with the appropriate values and configures the device. Later, it sets the status of the device to enabled. Similarly, when the monitoring component receives the new device event, it retrieves the configuration and the status of the device, and if the device is still not being monitored, it creates the appropriate KPI monitoring entities and configures the monitoring in the device to receive monitoring data. When monitoring is activated in the devices, periodically, the device component will receive monitoring samples that it will forward towards the monitoring component. The monitoring component will store these samples into the time series database, making them available for the Grafana panel to plot them. Regarding the creation of the connectivity service between both virtual network functions, the open source Mano delegates on the TeraFlow controller to first create the connectivity service and then populate the service with the appropriate endpoints corresponding to the different virtual network function connectivity points. As soon as the endpoints are added to the service component is able to compute the path for the connectivity service and populate the appropriate configuration rules for the different devices. To establish the connectivity service between the provider edge routers, the TeraFlow controller relies on the service component and the device component. First, the service component identifies which is the path between the two routers, finding which are the devices to be traversed. Then the service component creates the appropriate configuration rules for the different devices and delegates towards the device component for the configuration. In this case, the service component identifies that an optical connectivity service needs to be established over the optical layer to establish the connectivity between the routers. To establish the connection, the service component relies on TAPI for configuring the connectivity service. It populates a TAPI message with the values provided in the configuration set and sends the command to the OLS controller. When the connectivity service at the optical layer is established, then the service component creates the appropriate configuration rules for the different packet devices and populates these rules into the configuration set for that devices by means of the device component. In this example, it can be seen that three different sets of rules are needed. First, the configuration of the interface and subinterface, then the creation of the network instance, and finally the definition of the routing policies to be used for each of the network instances. We will now move to the demonstration. However, before that, we let you know that the source code of the TeraFlow SDN controller is available on GitLab, and some instructions about how to deploy, configure, and use it are provided in the same repository. We invite you to play by yourself with the SDN controller. In this tab, we have the web user interface for the TeraFlow SDN controller. Different sections are available in this web user interface. In the home page, we can choose the context we want to manage. Right now we have no contexts since the databases are empty. And we can upload the descriptor files for populating the list of devices and links we want to manage. Right now, we will do that because it takes some seconds to connect to the devices and populate the data structures. Right now that it is processing, we will inspect the rest of tabs. First, we have here the CTPC OS Interface that is in charge of managing the optical layer network. Here we have the open source manual web user interface dashboard, and we can inspect that right now we have no network service that is deployed. Also, we can check here that we have two WAN infrastructure managers for the two data centers that are connected, and we have here the OpenStack web user interfaces for each of them. As we can see, no instances are deployed in neither of them. Okay, now that we have the list of context topologies, devices, and links added, we can see here, which is the topology that we are going to manage. It is composed of two packet devices, two real packet routers, and two emulated packet routers. Also, it has an OLS that is used to interconnect the routers. Next, we will choose which is the context, because as it can be seen, no context is selected by now. Now we have the admin context, the one we created by means of the descriptors. Submit. And now we are in the admin context. So we can check in the list of devices, for instance, that we have the OLS using transport API, and the status is enabled. We have also one real packet router using OpenConfig, and the status again is enabled. It's the mission of the automation component to initialize and enable the different devices. One emulated packet router, the other real packet router, and the other emulated packet router. We can inspect here which are the details of the devices. For instance, we can see the list of endpoints. We can see the rules that are configured. Right now, we have the basic configuration rules with the settings for the endpoints. And we will also inspect one of the real packet routers. And we can see the types of port it has. We can also see which are the supported sample tapes for each of the ports, and we can see that for the packet routers, they can provide by now the input and output packet and octets. Also, if we go down, we can see that there are other predefined configurations for the interfaces, subinterfaces, and so on. Okay, in the links, we can see that we have 4 links that are used to interconnect the packet routers and the OLS. Right now, we have no services created. And if we go to the Grafana panel, we have one panel devoted for monitoring. We can see here that we started to get monitoring data as soon as we created the devices for the router 1 and router 3, and in particular for the 2 interesting ports for this demonstration. This traffic that we can see here comes from the traffic generator that is connected to both of the routers. However, we can see that in the link that is between the 2 routers, there is no traffic since the service, the connectivity service is not established. Now it's time for creating the connectivity service. For that, we will go to the instances. We will go to the network instances, create a new network instance. We will choose which is the network service descriptor. We will choose the default virtual infrastructure manager account, and we will choose the network service configuration. We can see here that in the configuration, we choose which is the mapping between the virtual network function and the VIM where we want to deploy that virtual network function. Also, we can see the mapping between the predefined networks, the virtual link descriptors in the NSD and the networks in the different VIMs. So let's create the connectivity service. Let's refresh. We see here that the service, the network service is under creation. Okay, let's wait for some seconds. Okay, now the network service is available. We can check here in the OpenStack instances that the instances have been created, and we can check them here. And for the second, okay, same happens. We can check here the instances as they are created. Next, we can check here and see that the network service have been created. 2 services have been created, as we explained it beforehand. One is for the packet layer, and the other is for the underlying optical layer. Let's start by the second. Here we can see that it is connecting 2 ports, and for these 2 ports, it is we can see here the specific configurations that are set. Then for the packet layer 1, we can see the settings for the service and the settings for each of the routers that are involved in this network service. If we go now to the Grafana panel, we can see that just after creating the service and establishing the connectivity, now we have traffic in between the two Infinera routers. The next step will be to destroy this connectivity service by destroying the network service. So here, we can click here on delete. Okay, and after some seconds, we should get our service destroyed. Okay, now the network service has been destroyed. We can check here
in OpenStack that the instances have been deleted. We can also check here in the services tab that the services have been deleted. And we can also check here that now we lost again the traffic between the Infinera routers, given that we destroyed the service.
Thank you very much for your attention. If you have any question or feedback you would like to share, please let us know. You can find us in the different links enumerated in this page or in the demo chat.